Section 3.4a, this is going to be part A, is going to be about linear programming. Linear programming is a topic that is probably new to you, and the foundation of it is that we'd be working with a situation in which there are limited resources, like maybe the materials we use to cook something or manufacture something. Other limited resources might be time or the amount of workspace that we have. And in addition to these limited resources, we're wanting to optimize something. So in other words, we want to either minimize the cost of producing something or maximize the profit that we are earning in a situation. So what we can do is we can figure out, of all the possible different combinations of creating products, what is going to use the resources in a way that will create the lowest cost to us or the highest profit to us. So let's get started. The first one we're going to do, what we're going to work on today, is going to be given the equations for the limited resources, their inequalities, and given the maximizing or minimizing function. And then in the next lesson, you will be working with a more real-world scenario where you'll have to make your own inequalities and equations. So for today, we're doing this guy right here. And it wants to know what point in the feasible region maximizes p for the objective function p equals 10x plus 15y. And then normally in a story problem, we'll only be asking for the maximum or minimum. But if it's not a story problem, it's just like this kind of problem, we can answer both questions. So we'll also be answering what point minimizes p, which is this function here. So let's talk about a little bit about the vocabulary that's going on. The feasible region is a fancy word for the shaded region that is created by this system of inequalities. So we already know how to create a shaded region from previous lessons. Now we just get to call it something different. So this is the shaded region. And then the objective function is this guy here, the equation. So the objective function is an equation that represents the thing we want to maximize or minimize. Okay. This right here is labeled constraints. It's actually, I'd rather label it system of constraints. That's usually how I refer to it. And that system of constraints represents the limited resources. When we're working in a story problem, the limitations that we're given create this system of constraints. So we have one inequality that says x plus y is less than or equal to 16, 3x plus 6y is less than or equal to 60, and then we have these two right here, x is greater than or equal to 0, y is greater than or equal to 0. And I want to talk about those for a moment because these two inequalities, when they appear together in a problem, change how we're going to approach graphing our system. So let's talk about these two together. Remember that x equals 0 is which type of a line? The x equals 0 is a vertical line, and y equals 0 is a horizontal line. X equals 0 is actually the line here. That's x equals 0, and this is y equals 0. So when we're working with a coordinate plane, x is greater than 0 or positive in quadrants 1 and quadrant 4. y is greater than 0, these are our y values, in quadrant 1 and quadrant 2. So when we put together these inequalities, that x has to be greater than 0, we could be in 1 or 4, and y has to be greater than 0 is 1 or 2. So when I have both of these in my system, that means that I cannot be in any of these three quadrants because both of those have to be true. So if you have x is greater than 0 and y is greater than 0, greater than or equal to 0, then we know that we will only graph in quadrant 1. So we can just make kind of this shape of graph, like a right angle, instead of all four. Now this often happens in story problems because x and y are going to represent some number of manufacturing items or like a number of cookies that I'm making or something like that. And so we don't want them to be negative because that wouldn't make sense to the problem. So we restrict our domain and range to this first quadrant there. Okay, so moving on to getting these graphed, I'm only going to draw the first quadrant, which gives me some extra room to make my graph in this teeny tiny space. So the first step in working through these problems is going to be to graph the constraints and shade the feasible region. I'm going to label this as x and this as y. If I had a story problem, I would want to label those with the actual items that x and y represent. When we graph, before we graph anything or make any tick marks on here, I want to go ahead and know how I'm going to graph these. Now these inequalities are written in standard or general form, and so we're going to graph them using the cover-up method. So I will cover up the y, and that gives me x equals 16. I don't use the inequality part when I'm getting my ordered pairs, so I just do x equals 16. So that's the ordered pair 16, 0, and then I cover up the x, that gives me y is 16. So that gives me the ordered pair 0, 16. And in order to know which side to test to shade on, I need a test point. So I will usually choose 0, 0 if that's possible. So I'm going to test 0, 0, putting in 0 for x and 0 for y gives me 0 is less than or equal to 16, which is true. So I will be shading that line on the side of my test point 0, 0. But before I put that on, I also want to know where my intercepts are for my other ordered or for my other inequality so that I know that I make enough tick marks. So I'll do the cover up method again. Cover up the y term. I get 3x equals 60. Divide both sides by 3. That gives me x equals 20. So I get 20, 0. And then cover up the x term. 6y equals 60. Divide both sides by 6. I get 0, 10. And then if I test 0, 0, 3 times 0 plus 6 times 0 is less than or equal to 60, which gives me 0 is less than or equal to 60, which is also true. So both of these will be shaded on the side of 0, 0. Now remember, these two just made me graph in the first quadrant, so I don't need to worry about doing anything with them at all. Tick marks. On the y-axis, I need to go at least up to 16. On the x-axis, I need to go at least out to 20. Uh-oh. there we go, no problem. Just make it a little bit bigger. And the y-axis 2, 4, 6, 8, 10, 12, 14, 16. Oh, we left out there. So as you graph my x plus y is less than or equal to 16, I put my ordered pairs on 16, 0, and 0, 16. And then I'm going to connect them. And since it was a less than or equal to, I will use a solid line. I don't need to go past the axes because I'm staying in quadrant 1. So there's that line. And it will be shaded towards the test point of 0, 0. So I'm going to indicate that I would shade in. And then my second one, 20, 0 over here, and 0, 10 up here. It is also less than or equal to, so it's going to get a solid line. And the test point 0, 0 was true, so I'll shade towards the test point, so in on that one as well. And then remember, on systems of inequalities, we're only going to shade the overlapping region. So the overlapping region is below the blue, below the green, and then of course bounded by those x and y axis. So it's going to be this little shape in here. Now it's important that you always do your test points because you cannot just assume that it makes this little shape, because it could have been this little section or this little section or this whole section out here. It all depends on which direction all of the inequalities are going. So make sure that you're doing test points. So step 1 is done. Graph the constraints and shade the feasible region. Step 2 is find the coordinates for each vertex of the region. Now a vertex is like the vertex of an angle or the vertex of a triangle or a square. It's like a corner, or it's where two lines intersect. So in my picture here, I actually have 4 vertices. I have one here, here's one, and here's one. Because I'm only looking for the coordinates for the vertex of the feasible region. So I have 1, 2, 3, 4. Now, we get lucky because you can eyeball where 3 of these vertices are located. So we already know where 3 of them all are. So we have the first one here is at 0, 0. This one here, the second one, that was one of our ordered pairs here. It is at 0, 10. I'm going to label this one 3 and this one 4. The fourth one we can tell is at 16, 0 because it was one of our points for graphing, 16, 0. But that third one, we don't know where that one is. We won't be using graph paper when we graph our linear programming problems, so you can't even kind of make a guess about where it is. I mean, we can kind of tell that it's in the neighborhood of about 11 or 12 on the x coordinate and maybe like 4 or 5 or something on the y coordinate, but we're going to actually have to find that intersection point. So I'm going to make a little note here that we don't know where this vertex is located. You cannot tell just by looking. And I don't mean that as a challenge. I mean that we have to prove where it's at. So we have to work for it. Well, how do we do that? How do we find the point where 2 lines cross each other? We've kind of spent several sections of this chapter working on that. So what we're going to do is we're going to set up, you know what this is, it's a system of equations. So we're going to set up a system of equations and solve it. Now, we've learned a few ways to solve them. The first way was by graphing. The second way was by using linear regression on the calculator, which was also still graphing. And we also have learned substitution and elimination. Those are the two algebraic methods, so that's what we're going to do here. We will use substitution or elimination. So I am going to figure out the equations for those two lines that cross right here. So for the third vertex right here, I'm going to set up a system of equations. My green line was x plus y, and we just change it to equals 16 when we set up this system. And then my blue line was 3x plus 6y equals 60. Now, you may have more than two equations on a linear programming problem, so you want to make sure that you get the correct two equations into your system. Let's see, equation 1, equation 2. I think that I am going to use elimination to solve this. So I'm going to take equation 1 and I'm going to multiply it by -3 so I can eliminate the x's. So that'll be -3x minus 3y equals -48. And then I won't do anything to equation 2 because those x's will cancel. And when I add those together, -3x and 3x cancel, and I get -3y plus 6y is 3y, -48 plus 60 is 12, divide both sides by 3, I get y equals 4, and then I'm going to sub that into equation 1, so x plus 4 equals 16, gives me x equals 12, so my ordered pair will be 12, 4. The next step is going to be to evaluate the objective function at each vertex. Now, the objective function was all the way in the instructions up here. P equals 10x plus 15y. So I'm going to write that down so I have it closer to where I'm working. And what we do to evaluate the objective function is for each vertex, so for 0, 0, 0, 10, 16, 0, and that last one we found of 12, 4, is we're going to substitute in the x value to the x spot and the y value to the y spot, and we're going to work it all the way to the end. So I'm going to have P equals 10, and then instead of x, it's 10 times 0, plus 15, also times 0. And then I work through that, 10 times 0 is 0, 15 times 0 is 0, so P is 0 in that instance. And then I go on to the next one. P equals 10 times the x value, which was 0, plus 15 times the y value, which was 10. And I work that through. 10 times 0 is 0. 15 times 10 is 150. So I get 150. And then 16, 0. P equals 10 times x, which is 16, plus 15 times y, which is 0. Equals 10 times 16 is 160. And then finally, with the point that I had to solve the system to get, P equals 10 times the x value, which is 12, plus 15 times the y value, which is 4. So that will be 10 times 12 is 120. 15 times 4 is 60. So that equals 180. So in step 3, we evaluate the objective function at each vertex. Now, why do we do that? This feasible region, the entire highlighted region, are all combinations of ordered pairs that make this system of inequalities be true or work. So all of the ordered pairs in there would be a legitimate solution to that system of inequalities. But what we're looking for is the one that maximizes or minimizes our objective function. So we could plug in a million different ordered pairs and then choose the one that's the highest for the maximum and choose the one that's the lowest when we plug it in for the minimum. But we don't have to do that. And the reason is that it's because you are guaranteed to find the maximum and the minimum value of the objective function at a vertex of the feasible region. So we don't have to plug in millions of points. We only have to plug in the vertices of the feasible region. So then we can make our statement. The maximum value of the objective function, well, to find the maximum value, you just look on there and find the biggest one. It's 180. So the maximum value of the objective function is 180, and it occurs when x equals 12 and y equals 4. The minimum value of the objective function, we just look for the smallest number, is 0, and it occurs when x equals 0 and y equals 0. Now when we work with actual story problems, we won't be saying that it's the value is 180. It will have units like the maximum profit is $180, and these will also represent things like the number of gizmos we create and the number of gadgets we create or something like that. So in story problems, these will be more like sentences, but for now, we're just going to use x and y values.